In this video, we will learn about reactions in which carbon-carbon double bonds, or more specifically the pi bonds, are nucleophilic and react with electrophiles. These alkene pi bonds are good nucleophiles in which the more electron density there is on the pi bond, the more nucleophilic that pi bond would be. So let me give you an example of what that looks like. So for a generic reaction, we'll talk about the detail of later. If I take an alkene, react it with bromine, the molecule bromine here, then I can get to this dibrominated product. So what you see is that both of these bromines get added across the double bond. What we can do is we can look at the relative rates of reaction of different alkenes with the same electrophile to help us get a sense of which alkene is more nucleophilic or more reactive. So when we have just ethylene, that turns out to be the slowest possibility on this chart at least. That gives a relative rate of just 1. And if we put one methyl group, so we'll deal with propene as our nucleophile, the reaction with bromine will happen 80 times faster, and so on and so forth until you get to tetramethyl ethylene here. That reaction runs 1,000,000 times, well, I guess 3,000,000 times faster than just ethylene alone. Finally, we can also see that by putting on resonance donating groups that make the pi bond more electron rich, so delocalization of a lone pair here that adds electron density to the pi bond, that can lead to even more significant increases in rate than just what we see here from adding alkyl chains. The explanation for this experimental observation is that there are filled orbital interactions once you add more alkyl groups, and these filled interactions are bad and overall destabilize the reacting pair of electrons. So what we're seeing looks like this. On paper, in the drawing, what we have is, here's propene, where I've drawn out the 3 hydrogens on the methyl group. What we have is there's a pair of electrons in the pi bond, and then adjacent to that, there's another pair of electrons in the carbon sigma bond that is sometimes aligned up in a way such that there is a little bit of mixing here, whether or not you like it. So again, the structure of the molecule forces there to be some mixing between a CH sigma that has electrons in it and a pi bond that also has electrons in it. What that ends up giving you is this type of a pseudo MO diagram where, again, I'm taking the filled sigma bond on the left, mixing it with a filled pi bond on the right. That's getting us to now essentially a splitting of energy levels where the sigma bond becomes, let's say, lower in energy, but the pi bond becomes higher in energy. This is because whenever two orbitals interact, you always get one a little bit lower, one a little bit higher in energy, and our orbital that's most similar to the pi bond is the one that's being raised. So then this is higher in energy than a situation where there's no such mixing. I want to also just show you what the computational model looks like, just to convince you that there is this interaction. So what I'm showing you right now is the pi bond for tetramethyl ethylene, and what I'll do now is to show you the CH sigma bond. And that is right there on the left, having shown up. And what you kind of see is that if I take this angle on it, you can definitely see where the two orbitals are mixing with each other in the middle. And that is the problem. This is unavoidable. All kind of alkyl substitutions onto an alkene will have this overall. And so the point here is that because these two orbitals are just so close in space, they are forced to interact, and that forced interaction causes a pair of electrons to go higher in energy than they would be otherwise if there was no such interaction. So in our reactions involving carbon-carbon pi bonds as nucleophiles, we'll see a few patterns or trends. We can kind of categorize all these reactions by the type of mechanistic intermediate that these reactions go through. And these mechanistic intermediates will then tell us what the regiochemistry of the reaction will be, or in other words, which of the two carbons of a carbon-carbon double bond are reacting. It will also help us decide what the stereochemistry of the reaction is, so whether one pair of enantiomers or all the possible stereoisomers or only one specific enantiomer or diastereomer is formed. And finally, we will also sometimes be able to see what are called rearrangements, in which sigma bonds seem to be just hopping from one place to another, and we'll see that in a minute. We'll look at all the different types of reactions in which an alkene is a nucleophile, and we'll do it by the mechanistic intermediate categorizations. So first we'll look at reactions in which there is a carbocation intermediate, and so these carbocations are going to form under very strongly acidic conditions. So for example, This is a hydration reaction where overall I have a double bond here, and I'm overall adding a molecule of water across the double bond. I say that I'm adding a water molecule across the double bond because I have the OH added to the top carbon, and then a second hydrogen is added to the bottom one. So in essence, I've added H2O. The mechanism for the reaction looks like this here. The first step, because we're under strongly acidic conditions, is to protonate the double bond. And that gets us to a carbocation here. So a carbocation is a molecule that has a carbon with a formal positive charge on it. And more specifically, it refers to a carbon with a formal positive charge with only 3 groups around it. This carbocation is then a very good electrophile, and any kind of decent nucleophile that's in the reaction can come in and attack that carbocation, getting us to the protonated alcohol and finally to the alcohol product after acid-base reaction. Something important to notice here is that this is an acid-base reaction using a pi bond as the base, or our nucleophile. And in this arrow right here, I have a choice to make in terms of whether I use the carbon from the bottom to bond to the hydrogen or the carbon from the top to bond to the hydrogen. And so that question falls under the purview of regiochemistry. So regiochemistry, again, being a decision about where in the molecule specifically we should react. So in these types of reactions where there are carbocation intermediates, there's going to be regioselectivity for protonating at the less substituted carbon. And so what that means is that in a reaction like this one, so I'm giving you a slight variation where I'm now doing what's called hydrohalogenation, in which now an HBr is adding across the double bond. Here I've made the alkene asymmetric because of this methyl group, and so now again we have that choice. And what we see when we do the reaction is that in terms of the products, there's a preference for putting the bromine on the more substituted carbon. And if we're looking at the CH2 up here, this is where the hydrogen goes, or that initial protonation goes. So that proton is going on the less substituted carbon. So we have a regioselectivity for a less substituted carbon when it comes to protonation. The reason for this is that this comes down to the stability of the intermediate. So if we think about a reaction coordinate diagram, we're going uphill to an intermediate. If we're going to a higher energy intermediate, then we should be thinking about structures like the intermediate for our transition state. So that's going to be these two possibilities here, where I've protonated either at the top carbon or at the bottom carbon. This causes there to be either a more substituted carbocation or a less substituted carbocation, where substitution refers to the non-hydrogens attached. And we'll get to this in a minute, but more substituted carbocations are more stable. And so that tells us that this intermediate will be lower in energy. That tells us that the transition barrier from the reactant to this intermediate is going to be smaller than the barrier from this reactant to the other intermediate. So this should be the faster reaction, leading us to more of this product here. Historically, when people first started studying these reactions and the regioselectivity of these reactions, someone named Markovnikov had their name associated with the outcomes. So for a hydrohalogenation, the Markovnikov product is the one where the nucleophile ends up on the more substituted carbon, or viewed conversely, it's the one where the proton ends up on the less substituted carbon. And so the opposite situation is then called the anti-Markovnikov product. So again, the Markovnikov product has the nucleophile on the more substituted carbon. There is a problem with this terminology. This terminology persists to this day in various standardized exams and in various textbooks, but it is essentially only really applicable to this reaction. The concept is that we're thinking about the electrophilic hydrogen going to the less substituted carbon, nucleophilic bromine going to the more substituted one. That's always going to be the case. The electrophile will go to the less substituted carbon, and the nucleophile will go to the more substituted carbon. The problem is that we can do various tricks to make the position of the hydrogen and the bromine here be swapped. So I could use nucleophilic hydrogen and electrophilic bromine in a way. And so when people refer to Markovnikov and anti-Markovnikov products, they may not actually be thinking about how the mechanism for that reaction works. This kind of conflict of ideas will make sense as we start to see some cases of anti-Markovnikov selectivity in future videos. The second consideration for additions to an alkene are that because we're adding two groups to an alkene, then there is this possibility of the formation of stereoisomers. So for example, if I take trans 2-butene here and expose it to hydrobromination conditions, then I can make both enantiomers of the 2-bromobutane product, because I can either have the bromine end up being wedged here or hashed. The hydrogens, the one that I'm adding is either wedged or hashed, but it doesn't really matter because they're both hydrogens on that CH2. To understand what might be happening in this reaction, we have to look at the intermediate. So the intermediate looks like this, and if you're looking at it, the electrophile is this p orbital, which is kind of the same above the molecule as it is below the molecule. And so what that means is that as this carbocation is floating around, and a bromide is kind of floating around nearby and colliding up by chance, there is an equal probability for the collision to happen from the bottom face as there is from the top face. What that means is that essentially I'm able to put in either a wedged bromine, if I do it this way, or a hashed bromine, and do that with equal probabilities. Therefore, I get to an equal amount of both enantiomers, and therefore I have a racemic mixture. And so what we say is that there is no stereoselectivity inherent in this reaction mechanism. There might be, in more complicated molecules, other reasons we would prefer to react from one end or the other. So then we would say that there would be stereoselectivity, but it's not because of the reaction mechanism itself. It's because of other external factors. A third consideration for all reactions that have a carbocation intermediate, not just an electrophilic addition to an alkene, is that there are carbocation rearrangements. So carbocation rearrangements occur to allow the molecule to be in a more stable carbocation state. And so the reason that we know that this is the case is because if we take an alkene like this one, so 2-methylbutene, react it under hydrobromination conditions, what we get is some amount of the expected product, where I have the nucleophile adding to the more substituted carbon, the hydrogen on the less substituted one. But in addition to that, you might see, often in the majority amount, a totally different product, where the nucleophilic bromide appears to have attached to somewhere where there was no electrophile in the original molecule. And so if this is what you observe, then that's a sure sign that there has been a carbocation rearrangement going on. So let's look at the mechanism to understand this. So we start off the same way as we would for any other analogous reaction. We protonate the pi bond. That gets us to the carbocation. And at this carbocation stage, we have to be a little careful, and it is always helpful to fill in all of our groups here. So what we're going to see is that there is a rearrangement, and that rearrangement overall, what it looks like on paper is that I've taken a positive charge and moved it to an adjacent carbon. But in reality, because we don't think about positive charges moving, we think about electrons moving, then what I'm really doing is I'm removing a pair of electrons from the tertiary carbon and having that jump over to where that carbocation is. So this does not count as a nucleophilic reaction, but it has that sense to it. So this pair of electrons has just essentially slid over. And so the way I will view that is, if I kind of draw in all my groups again, is that that pair of electrons looks like this. So the hydrogen atom actually doesn't have to move very much. It's like the electrons kind of just slid over. I kind of view it as like a door kind of turning. So if the hydrogen is at the vertex up here, the pair of electrons is just kind of going over. This rearrangement occurs because the tertiary carbocation is much more stable than a secondary carbocation. We'll get to the reason for that in a second. But once you have that species, then the nucleophilic addition of the bromide to the carbocation takes place to get you to product. And so if you're thinking about why you still see both of these, basically what you have is, once you form this intermediate, there are now two different things that can happen. Either by chance this can collide with bromide right away and form the product up here, or if there's enough time, a rearrangement could happen before any collision with bromide, and then the bromide collision could happen, forming the second product. And so in every reaction, there's just this kind of unknown balance of what the rate of rearrangement is versus the rate of colliding and forming the major product. In general, the assumption is that rearrangements are pretty fast because they happen just within a molecule. You don't need the molecule to be oriented in a very specific geometry and in a certain way of collision for the rearrangement to happen. And so we think of rearrangements as being relatively easy. The collision to do an actual reaction between two different species is a little bit more difficult, just kind of entropically speaking. So back to this idea of more substituted carbocations being more stable. The reason this is the case is because of hyperconjugation. We can look at a comparison between methyl cation versus tert-butyl cation here, where the carbon that is cationic has either no alkyl groups on it, or here 3 alkyl groups substituted around it. What we're really seeing is this comparison. So for the methyl cation, we have the empty p orbital and just 3 hydrogens out to the left. For the tert-butyl cation, again, we have an empty p orbital, but we have all these adjacent pairs of electrons that are in the sigma CH bonds. So I'm going to draw them like so. And so each of these can kind of mix a little bit with the positive and empty p orbital. And since we're doing a filled empty interaction, that is going to be overall stabilizing. This is what hyperconjugation is referring to, and this is what stabilizes carbocations that are more substituted. As a general principle, what we'll see is that tertiary carbocations are reasonable mechanistic intermediates. Secondary carbocations are kind of iffy. Primary carbocations are very unstable, so even if they form, they almost always will rearrange right away to form a secondary or tertiary carbocation. A second type of mechanistic intermediate that forms when alkenes are nucleophiles are during the reactions between alkene nucleophiles and halogen molecules, so kind of X2 species here. The intermediate is called a helonium, and we'll see that in a second. So an example of such a reaction would be the halogenation of a pi bond, where I can take my cyclohexene, react with a molecule of bromine, get to this racemic mixture of dibromo cyclohexane. So let's look at the mechanism. It looks like this. I'm going to fill in some lone pairs here to help us track everything. So what we're going to get is that the nucleophilic pair of electrons will attack bromine. That attack is to the bromine-bromine sigma star orbital, because this is a sigma bond, so we must be attacking the sigma star orbital. That thus causes that bond to break. At the same time, we get this kind of a biting back, where a lone pair from bromine here kind of comes back to fill in the void. So if you think back to protonation of an alkene, you end up with a positive charge on one of the carbons. Here, because bromine is really big and has this pair of electrons available, that can come back and essentially fill the positive charge that would have been formed by just the first arrow here. So we do both of these arrows to get to this 3-membered ring, which is our bromonium. If we're keeping track of everything, we should have electrons like so, where we have our bromonium ion and then a bromide that has left. In the next step, you can imagine that this is not the most stable species in the world. Most of the time, it's not possible to isolate this. It's just a reaction intermediate. And so as soon as the correct collision occurs between a nucleophilic bromide and the electrophilic sigma star of a carbon-bromine bond here, then we can get the breaking of the 3-membered ring that relieves a bit of strain. That gets us to the product where I've shown it as this specific enantiomer, but I do have the racemic mixture nonetheless. This reaction will take place regio selectively, and so what that means is that, again, our nucleophile here, this bromide, will have a preference between the 2 different sides of the 3-membered ring, depending on what the structure looks like. So for example, another analogous reaction is halohydration, where if I have additionally some water present along with my bromine here, then I can actually get the nucleophile to be the water molecule that adds in. So first I get the electrophilic bromine, then nucleophilic water. Here, what you'll see is that the water has preferentially added to the carbon that is more substituted. And so that should make you think of the previous set of reactions in which we were putting the nucleophile in the more substituted carbocations. So let's look at a mechanism again. The initial part is the same, so we have attack of the pi bond onto bromine, bromide leaving group, and then kind of an attack back by the bromine. That gets you to the three-membered ring, Helonium ion. The reason that there is this preference now for the water to attack one of the carbons over the other is that actually when we are considering the molecule, what we're really thinking about is that there is going to be some amount of positive charge that can be associated with either of those two carbons in the three-membered ring. And so if we're thinking about the molecule trying to have a bit of partial charge on these two carbons, well, we just talked about how we like to have carbocations that are more substituted. Analogously, we like to have partial positive charges on our more substituted carbons. That's a more stable way to have our structure. And so what that means is that, and so what that looks like in the structure is that actually what we get is a skewed three-membered ring instead of an equilateral one. The carbon that has the more substitution on it is much happier being a positive charge. So you can almost think of this as being somewhere between a structure that looks like this and here, right? So it's not really resonance form, but we're thinking about the fact that we're somewhere halfway in between this, right? And so what that results in is this lengthened bond where there's some amount of positive charge on this carbon that makes this carbon more electrophilic. That means that the nucleophile is more likely to attack here, getting us to our major product. So we have regioselectivity. I want to show you what this looks like from a computational perspective. How much of a skew is there really to that three-membered ring? So this is the structure of that bromonium ion for this reaction here. And so if I kind of turn things around here, what you see is that the skew is pretty great. The bromine is really leaning over to the less substituted carbon because the more substituted carbon can handle more of that partial positive charge. So there is some regioselectivity in these reactions. There is, more importantly, also going to be stereospecificity. The ring opening step where the helonium ion is broken open, that can occur only in one way, and so we call that stereospecific. That stereospecific process then forms anti-stereoisomers, and this is all because the sigma star bond that we're attacking with our nucleophile is necessarily pointed in only one direction and none other. For an example of this, let's look again at the bromination of cyclohexene. Cyclohexene reacts with bromine to get you to the anti-stereoisomer product, and you get both of them because if you look at the intermediate, you could react from either side. So I can react from the top side here where there's a sigma star, and I can react from the bottom side as well because there's two equivalent electrophilic orbitals to attack. The other possible product of this reaction, in theory, would be the one where both bromines are kind of either both wedge or both hash. Those are the same thing because this is meso. This is the syn product. This is the syn product, and we don't see this formed essentially at all in this reaction. At least it's negligible to the point that we can ignore it. And so because of that, again, this is a stereospecific reaction, and we are specifically forming the anti-stereoisomers. Before I end, I want to take a deeper look at the mechanism for halogenation. It turns out that what I just told you about the mechanism is wrong. This is going to be the mechanism that you see in essentially every textbook, in all of your standardized exams. You're going to see that the mechanism is going to be an alkene attacking a single molecule of bromine, forming a helonium and a bromide leaving group. That turns out to actually be totally incorrect. So if you try to go and model this, the modeling actually tells us that this is not electrophilic enough and the other bromine is not a good enough leaving group to have this reaction happen like this. And so what is actually happening? Turns out the experiment also tells us that this mechanism is wrong. So the reality is that there needs to be two molecules of bromine involved. And so the reaction actually looks like this, where we have the same process forming the helonium. The leaving group, however, actually goes and does something like that, where the bromide is never alone as an ion, but rather attacks a second molecule of bromine, forming this species here, which is called a tribromide, in addition to the helonium. For the purposes of this class, it will be fine to do the initial mechanism that we talked about that followed this kind of a pathway, where we had again this attack and leaving group leaving like that. But especially if you go on to study chemistry in the future, it is helpful to know that this is actually what's happening. A lot of our reactions will be like this. There's going to be the core piece of what's going on, and then there's going to be kind of a surrounding cast of other species. A lot of the times it's just the solvent molecules. Sometimes it's a second molecule of whatever else it is that might be either hydrogen bonding or accepting the leaving group. But I guess my point in the end is that we are going to focus in on the most important details of the mechanism, but try not to forget that there are a lot of other things surrounding these molecules when they react. They are not isolated in space. So that was a look at two types of electrophilic additions to alkenes, where we categorized these reactions by mechanistic intermediate. So far we've looked at hydration reactions and hydrohalogenation reactions, and additionally looked at the formation of helonium ions and how those are opened by nucleophilic attack. In a subsequent video, we'll look at some more different mechanistic intermediates that are formed in these reactions.